Okay, so let's talk about heat. Here's just an outline of what's in the chapter. We're going to start by mostly defining stuff. And anybody know what this picture is?
It's like a heat sensor over here.
It's a heat map, right?
Yeah.
It's infrared, and it's actually the cosmic microwave, it's actually microwave, background radiation. It looks like a heat map, though. Does anybody know what that is?
What?
Okay. All right. So let's talk about temperature and some definitions. So temperature and thermal equilibrium. So let's say we have system A and system B. Yes?
So for the space thing,
Oh.
can you see the Luxor in the hotel space, like that light? I know it's probably horseshit, but like, how long would that take to travel, like through like, the atmosphere and into space?
Well, you just have the distance multiplied by the speed of light. Okay. I mean, distance time, right? So, the Luxor has a spotlight that travels at a speed of c, which is 3 times 10 to the 8th meters per second. The atmosphere, that's about, is it like a 30,000 feet about? So, like 10,000 meters. So you can calculate how long it's going to take for it to get out of the atmosphere, right? Because you have meters per second, so you take 10,000 meters divided by c. It gives you how long it takes for the atmosphere for it to leave Earth. If you want to figure out how long it takes to get to the next planet, you can calculate that too. Mars signals with light, it's about 14 minutes, I think. A little bit farther. Which is why having a remote control vehicle on Mars is sort of problematic, right? Because the remote control car, how does a remote talk to anything?
Right. Radio waves.
Waves. What kind of waves?
Radio.
Radio. What kind of waves are those? Oh, no, they're electromagnetic, right? Radio waves are just a form of light. Light it has like the human definition, which is like crap we can see, but light in terms of physics is all electromagnetic radiation. So that includes radio, gamma, all of that stuff. All of it travels at the same speed. That's the speed of light. So radio waves can only travel at the speed of light.
They don't really control it remotely. They input what they wanted to do, and then hopefully they got it right.
Right. That's what they do,
Yeah.
right? You don't want them to you don't want to look at the camera and be like, okay, drive forward, and then you look at the camera again, you're like, oh shit, a cliff. You know, that's sort of the issue that they're dealing with.
What happens,
so there's
right?
that's happened, right? They've like gotten things stuck in sand
shit,
dunes.
it's 8
And,
meters,
anyway,
not 18.
okay, but yeah, be careful. I forget where I was going with this. Anyway, if you look into space, you look into the past. So it's interesting. Anywhere you're looking, you're looking into the past. The farther you look away from you, the farther in the past it is. Okay? So distance is time. Yeah. If you want to spend more time thinking about that, take Physics 210. We can philosophize about it a little bit longer. But the other messed up thing that makes everything difficult is the speed of light is the speed of light no matter how fast you're going. So let's say I'm on a cart and I throw a ball, right? What's the speed of the ball if you're standing still? Yeah, speed of the cart plus the speed of the ball. What if I shine a flashlight? What's the speed of the light according to you? Right. It's not the speed of the cart plus the speed of light. It's just the speed of light. How do you make that work if you have to use kinematics? That's called special relativity. So, fun times. That's just a major correction because we have to make light constant. Right, the way we started doing things is we thought time was constant, right? Time is the same for everybody in every reference frame. It's not true. Time changes depending on whether you're moving or not. All right.
I think we're brains.
And we learned that in Physics 210. Anyway, let's talk about what's crazy is like, it sounds like new and spooky, but we've known that for like well over 100 years now. The whole Einstein was like, got fired from his university job, worked in the patent office, and then put some math together for Maxwell. Anyway, speaking of physicists who were terrible at math, Einstein, if you think you're bad at math, he was very bad at math. And now he's the only one anybody knows.
So you're saying there's a chance I'm a genius?
Wait, what?
I have a poster down there of Einstein. It's like, it's like whatever struggles you're having in math, like showing you mine are far greater. Like,
Yeah.
makes sense.
You know how he got his papers together?
No.
His wife did all his math. He just copied off of her work. And then he gave her half his Nobel Prize money, but she didn't get credit for anything. But she was in his like grad school class, and he married her, and then she had babies, and his like people were like, "You can't do science because of babies." And then you know,
You have ovaries. Like,
yeah. Yay, passed. Okay. Instead of me, you could have some old Russian guy up here. So system A, guess what temperature it is? Cold. Yeah. System B, hot. Good job, guys. All right. And I should have put that up first. So let's put it in a cooler. All right. So let's put it in like a Coleman or whatever. All right. This is what we call an isolated system. Why do we call it an isolated system? Because the heat isn't crossing outside of the system. So it's isolated from the environment. Remember, system, environment. So that stuff's still going to be valid. All right. Let's put an insulator between them. Like some styrofoam or something. Okay. Wait some time. What happens? Let's assume this is a really good cooler and a really good insulator. Nothing happens, okay? Because there's no way for the temperature to change places, okay? Now we put the same system in a cooler, but we put like a piece of metal between them. Okay, so like maybe this is a steak, and this is a frozen steak. This is a hot steak. I don't know. This is a piece of metal in between them. What happens to this system after you add time? Yeah, they reach the same temperature, and they're both warm, I guess. Like, lukewarm steak. Uncooked lukewarm steak. Okay, you should probably cook it. All right. So two systems are in thermal equilibrium if and only if they have the same temperature. So thermal equilibrium sounds fancy, but what does it mean? They have the same temperature. So if I say that this box of nerds is in thermal equilibrium with the desk, what does that mean? What's their temperature? Equal. And actually, we can figure out what it is. So apparently this room is 71 degrees. Okay? So lots of things in this room are in thermal equilibrium, which means what temperature are they? 71 degrees. Now, which sorts of things? The same. Yeah. You're pretty. What temperature is the chalkboard? 71 degrees. What temperature is this desk? 71 degrees. What temperature is this pen? Probably 71 degrees. What temperature? This is colder. What temperature is? But if we leave this here for a long time, what temperature will it be?
71 degrees.
71 degrees. Now, what about you guys? Are you in thermal equilibrium with the room?
No.
How long will we have to leave you here to be in thermal equilibrium?
However long you start and die.
Long enough to die, okay? Because you generate heat, so you're not going to end up in thermal equilibrium. But if you set your pen on you for a while, it probably reaches thermal equilibrium with you, okay? And actually, the room will warm up a little bit, but since you're still generating heat, that's a little bit different situation, okay? But things that don't make their own heat reach thermal equilibrium with the stuff around them. Okay, and so everything in this room that's not making its own heat, so aside from like the lights and the computers and all the electronics and the people, should be at about 71 degrees. All right? Okay, so basically you achieve thermal equilibrium by putting systems in thermal contact, and systems, remember, can be anything. So this is a system. This is a system. This plus this can be a system. It's whatever you want it to be, okay? So the zeroth law of thermodynamics, I know, there's 1 and 2, but I like to call this one 2. So the not first, it's right before the first. Basically, if you put any systems in thermal contact, right? If A and C are in thermal contact, and C and B are in thermal contact, technically they're all in thermal contact. Okay? It's the transitive property of thermal equilibrium. All right? So, yeah, basically if you leave stuff long enough, it'll all go into thermal equilibrium. Some things longer than others, like people have to die first. But, you know, that's like a non-infinite amount of time.
Probably a couple days.
Well, if we don't feed you, take at least a couple days.
I think the water's
We have plenty of water, so yeah.
not gonna be any good though.
Okay, well let's stop trying to talk about killing people. We don't want that on record. Here we go.
Is this some crazy?
I don't think it's hidden. I think it's just in the computer.
Yeah.
I want you to think about which of these answers is always correct.
We're gonna be all over the place.
Why is there a hyphen?
We're gonna be all over.
Because I copy and pasted.
Hard emphasis on tempera.
Yeah, temperature. Now I'm hungry.
Yeah, I told you we're gonna be all over the place.
All right, okay. All right, let's discuss this and vote again.
So what did you pick? You picked D? Yeah. Yeah.
Okay, so
That's what I'm saying. I picked C. But
No, the tip. If you look at it a little bit.
a weighted average, why weighted?
They have like, right, that's what conducts the heat. The mercury though, is what reacts to, that's right.
Yeah, but that's yeah. What he's saying about breakers,
Talking
that's
about my
assuming
half and it's just-
so this is assuming you have mercury.
It's common back
Yeah.
Oh,
I say C, man. It's like, you know.
That's no, they don't all have mercury. Yeah, you're right.
Okay.
Okay,
again.
Let's see. Let's see. I know, it's okay. She's smarter.
It's better. Okay. So think about your little liquid thermometer. All right. What happens right when you put it in the hot water? It starts moving. Okay. So right when you put it in the hot water, does it measure the temperature of the water? No. What does it measure the temperature of?
The thermometer?
The thermometer. Okay. Now, when do you stop? What do you wait for when you're trying to figure out the temperature of the water?
The thermometer stop?
Till it stops moving. What would you call that? Thermal equilibrium. Okay. So you read the temperature of the thermometer, but you know it's the same temperature as the water when they're in thermal equilibrium. Okay. All right. So let's talk temperature scales. Here's how some basic thermometers work. All right. So here's the thermometer we were just talking about. It's usually glass. Why do you think it's glass?
Easier to absorb.
Is glass a good conductor?
No, it's just easier for transfer of heat.
So, yeah, it's actually a good insulator. But what about this part? What do you notice about this part?
Bigger.
It's bigger. It's thinner, right? So the thinner the glass is, the more easy the heat conducts better. Okay, the heat transfers better. Why is it thick here?
So that way it doesn't.
That's what has the most
It stays there longer.
The heat doesn't go out, but also, like, imagine you're putting this in a pot of water and you're holding it with your fingers. Do you want to measure the temperature of you or the pot of water?
Hot water.
Pot of water. So you don't want anything touching the upper part of the thermometer to affect it, because you're not putting the upper part of the thermometer in the thing you want to measure. Okay. So you want the thin walls where you want to measure things, the thick walls where you want to not measure things. Okay. Container of gas. What happens if you heat up gas?
It expands.
Expands. Okay. So this basically uses pressure to give you temperature. All right. This is just a piece of metal. If you heat up metal, it also expands, and then it changes shape, and it changes the dial. Okay. Tricky part is calibrating those. It's fun times. Okay. So let's talk about temperature scales. So let's start with, we know this is all water, right? So this is freezing water.
What?
Come on. Liquid water and steam. All right. So this would be the freezing point. That's when water and the ice are the same, and then boiling point. I know, this is very basic, but come on, it's a test day, so I wanted to take it easy on you guys. So we have this temperature scale we use, which is very intuitive. Obviously, everybody knows that things freeze at 32 degrees, and when do they boil? 212, and absolute zero is at negative 459.67. Which makes so much sense. But if you want to not be totally frustrated all the time, it's better to learn to transfer Fahrenheit into Celsius or Kelvin. Okay. So good old Lord Kelvin. Celsius shows some important things for water. Water freezes at 0 degrees and it boils at 100 degrees. And why do humans care so much about water? Yeah, mostly so we don't die. But we're made mostly of water, and we cook with water, and yeah. Most of our planet's covered in water. Soon to be more. All right. Yeah. I am really excited about Waterworld. I'm going to find dry land. All right.
You live on Point Loma, you'll be fine.
For now. So negative 273 Celsius, not great, but that's where absolute zero is. And then if you want to do Kelvin, you notice this scale has a slope to it, and this one, the slope is 1, which is much nicer. So this is a Celsius and Kelvin have a degree-to-degree map. Just don't use Fahrenheit, it sucks.
It's the worst.
It's the worst. Thanks, British people. And so, yeah, there's Kelvin. Kelvin just starts the scale at 0. Now, what does 0 Kelvin mean? What does 0 degrees? What's absolute 0 mean?
I mean, yeah, everything, there's no vibration.
Yeah, the molecules that make up whatever you have, they're not moving anymore, okay? So temperature always has to do with molecular motion on the microscopic scale, okay? So if you have a gas, right? Well, we can act it out, right? So a gas is going like this, and then if it's liquid, it's moving a little bit less, and then if it's a solid, it's just vibrating like that, okay? So, yeah. Thermal energy is 0 is when we have absolute 0. So temperature is only 0 when thermal energy is 0, which means the kinetic energy of your gas, meaning the motion of your gas, is 0. Okay, so even the little tiny atoms aren't moving at all, which is kind of crazy. They're always kind of moving. All right, and the closest we've ever gotten to absolute 0 is 0.0000000045. So 450 picokelvins. So a lot of zeros. So 0.000045. Okay, just small, but not exactly 0. And that's because the molecules were still moving a tiny, tiny, tiny bit. And the main way you get down to those sorts of temperatures is you find some way to evaporate off any of the molecules that are moving too fast. So you trap the ones that are moving, and then the ones that are moving fly away and you ignore them. They're not part of your system anymore. You just have to have enough that are not moving. They call that laser cooling. But anyway, yeah, it is. Well, you just have to get them out of your system, right? Just cross the border, they're gone. Okay, so let's talk about expansion. All right, so here we have linear thermal expansion. So here's our thermometer. Here's a little bar of length L0, and we raise the temperature, and the bar gets longer, okay? And it gets longer with this equation. So here's the change in length. Here's your original length, all right? Here's your change in temperature, and this thing is called the coefficient of linear expansion, all right? And guess what that depends on?
On
the material, right? Yeah, the material. Because if this is metal It expands differently than if it's concrete, which expands differently than if it's plastic, and so on and so forth. So alpha depends on the material, all right? And so just microscopically speaking, right, all particles in a solid vibrate even when it's cold, unless you've gone down to absolute zero. The hotter you make them, the more vibration they do. And since they're bonded together by molecular bonds, you can think of those as little springs. Okay, if they start moving faster, they can stretch the spring a little bit farther, and if that's a whole lattice structure, the whole thing gets bigger. And so it actually doesn't just get bigger in length, it gets bigger in all directions, but this just takes care of length. We also have an equation for like a bulk expansion, like a volume expansion. But depending on the application you're doing, if you're building like a bridge or something, you might need the linear expansion, you might need the bulk expansion. Okay? And here's some so for different materials, right? Aluminum has an alpha of 2.4 times 10 to the negative fifth. These are in Kelvin inverse because you have to cancel Kelvin to get meters again. See what I mean? An invar? Yeah, sure. Okay. Steel, quartz, glass, all those things. All right. You heat them up, they get bigger. They get bigger by this coefficient. Yeah. What? Yeah, if you make it colder, they get shorter. So, yeah, this can change sign depending on the sign of this. All right. Anybody ever seen one of those?
Yeah.
Yeah.
Why?
What do you mean why?
Why is this here?
Sorry, to account for expansion.
Yeah, to account for expansion, right? As the bridge gets colder and hotter, maybe not so much in Southern California where our temperature range is a balmy 20 degrees, right? Like, oh, it's freezing, it's 52. Some places have a much bigger temperature range, and so your bridges and things will expand and contract depending on the temperature. You don't want things that expand and smash into other things, because what happens then? Your bridge falls down, and then everybody dies, which is bad. So, yeah. Anyway, this is... we don't need to know this, but I'm showing you this in case you like engineering stuff. So this is force over area. Anyone know what force over area usually gives you?
Yeah.
Kind of. It's pressure, but it also is sometimes called stress. This is something called Young's modulus, which also depends on the material. This is your coefficient of linear expansion. So these are both material-based constants, okay? This has to do with the elasticity, this has to do with the thermal expansion, and this is the change in temperature. This is the force, cross-sectional area. Yeah. So like if you cut the bridge like this and you looked at the cross-sectional area of the bridge, you'd have the force over that area. That would be the pressure the bridge would feel, and you can measure it with a pressure sensor. Okay. All right. You can also have volume thermal expansion. It looks pretty similar. Your change in volume is now this coefficient times V, your original volume, times change in temperature. And this is your volume expansion coefficient, okay, which is also dependent on material. Yeah. So, what? Glycerin, yes. 49 times 10 to the negative fifth.
Sounds good.
Oh, yeah, there's a demo here that you can do, right, if something expands. So you can get, there's like a ring and a ball. We could do this. I think we have some back there. But you can stick the ball through the ring, and then once you heat the ball up, guess what? Doesn't fit. Yeah, that's what she said. Okay. So, here's a fun question. What happens if ice sinks, like specifically to this fish? Yeah, that's correct.
Smash.
So, fish smash. I actually made an animation for this. Oh, wait a minute.
Oh no, he's belly up.
So, most things, when they turn into a solid, become denser. Fortunately for us, water does not do that, okay? In a temperature between 0 and 4 degrees Celsius, it decreases in volume with temperature. Sorry, increases in volume with temperature. Water does. Sorry, water expands, and then the ice floats. That's the main point. Ice floats, okay? Yeah. So above 4 degrees Celsius, water expands when heated. So anyway, water has its greatest density at about 4 degrees Celsius. Just throwing that out there. But this is the key to life on Earth, because if you subscribe to this theory of evolution thing, where did everybody start out? Yeah, swimming around in the sea like a fishy. Okay, so microorganisms in water. If everything freezes and the ice falls on it, then not a lot of life survives. Okay. Fun fact. Guess which part of the electromagnetic spectrum you can see underwater? Like if the sun shines on water, which part gets through? Not much. Yellow? It's actually
Gamma.
gamma. No, gamma. It actually
talking about
filters
colors?
gamma.
No, it's
Yeah, the colors get through.
Oh.
So if you look at if you look at water, it absorbs infrared. It absorbs UV. You know what it doesn't absorb? Light, like the visible spectrum, which is sort of the idea, like that's probably why we see in the visible spectrum, because if you develop the ability to see things while you're underwater, it's not very useful to be able to see infrared or gamma or UV because you're not going to get any. Okay, so out of the things that from the sun that make it underwater, pretty much just the visible spectrum. Yes.
About surface tension. You're talking about things that float. How like a leaf floats on the surface. And why is that not why ice floats, or?
No, ice doesn't float because of surface tension. Ice floats because of density. We'll talk about buoyant force when we talk about fluids, but that has to do with the relative densities of two things. So, for instance, that's why oil floats on top of water. It's not surface tension, it's a density issue. Well, those are two separate issues. So it's less dense and hydrophobic. So it doesn't mix well, but it also floats. So for instance, if you shake it up, right, you can see it forms little balls, and all the balls float back to the top. So it's two separate issues, yeah. Okay, so let's talk heat. All right, so heat. Let's go back to our conservation of energy issue. All right, this is what we just learned, right? So the external work is equal to all this stuff from the isolated system. So change in potential energy, change in kinetic energy, and thermal energy, which up until now has really just meant friction. Okay, but what happens with friction? What do you get? Heat. Okay, so it turns out, so this is any external force acting on the system. Okay, so once you define the boundaries of your system, anything coming in from the outside. This is any change in height or stretching of a spring. Okay, this is any change in speed or rotational speed, and this is any change in thermal energy. Now remember, what is this made up of? No, so microscopic forces and energies, right? So this is made up of microscopic potential energy and microscopic kinetic energy. So for instance, thermal energy, if it's heat, that's because the molecules are moving faster. That's microscopic kinetic energy, okay? You can also store thermal energy in like the springs, which are the bonds of atoms, okay? That's a kind of potential energy that can be included in thermal energy. So we have all these things, okay? Yes?
For thermal energy, why is it's changing thermal energy, but why is there no delta?
Oh, that's just a stupid notational thing. You can write a delta. Sometimes they write a delta. Sometimes they don't write a delta. And it's mostly just to confuse you. Yeah. Anyway, how do we measure change in thermal energy? Guesses? Temperature. Temperature. That's the only thing we really measure, right? It's hard to measure energy. How do you measure energy? Do you have an energy meter? No, but we have a thermometer. Thermometer? It measures temperature. Okay? So there's certain things that are easier to measure. If we want to know about the thermal energy, we measure the temperature. So temperature and thermal energy are linearly related. If temperature goes up, thermal energy goes up. If temperature goes down, thermal energy goes down. Okay? And we'll talk about the exact relationship later, but you can assume that they're related. Yes?
Isn't that why it's in joules? Because in the joule, the amount of energy it
But it's not very easy to measure energy. It's pretty easy to measure temperature. You could probably do it with your phone right now, but your phone doesn't have like a joule meter, because like do you know how we get? Do you know how we get? Do you know how we get calories for food?
Calories from food?
No, like how do we measure how many calories are in a food? Yeah, you just light it on fire, and you measure the temperature difference.
Somebody just like cooked up a steak. All right, now let me just keep it on the grill.
Let's see how many calories this is. Yeah. No, but you put it in.
Light the whole cow
You
on
put it in an
fire.
isolated system. So you put it in an insulated container, burn it, incinerate it, and you'd measure the temperature change. Yeah, that's it. Actually, if you just Google like burning, well, just light some gummy bears on fire, then you'll realize that
like,
so many calories in sugar.
do they cook it first and then do it? Because like
Yeah, because if you like go to that stupid Live Strong app or any of those food apps, there's different calorie counts for cooked and uncooked vegetables.
I know, that's what I was saying. Can you
Yeah.
imagine being that asshole chef who's like working for like 6 hours a day making all this food?
I don't
And he
think.
walks into the room and they're just lighting it on fire. It's like, what the fuck?
I think it's just like one lab that does like everything, but whatever. Okay, so anyway, if you want to measure thermal energy, I'm glad that you're really excited about this. If you want to measure thermal energy, temperature. Okay, so if you want to know if the temperature is changing, measure the temperature. Sorry, the thermal energy is changing. Measure the temperature. Okay. Work external means you have some external force. So in this case, we have this insulated container with this really weird. This is clearly a contraption from like the 1870s. Okay, but it is actually an experiment that somebody did. So it turns out if you really well insulate water and you stir it, what happens to it? It gets hotter. Yeah. So when you stir your hot coffee normally, why does it cool down? Yeah, you have the top open, right? You can't really cool the coffee down with the top closed. So you open the top, you stir it, and that's actually just allowing more contact between the fast-moving molecules, and they evaporate, and then you get cooler coffee, okay? Evaporative cooling. But if you insulated the coffee and then stirred it, you can actually make it hotter, all right? Yeah. No, hot. All right? So anyway, if this is considered your system and the boundaries are this little thermos thing, right, you have some external work being done on the system. Is there any potential energy? So change in height, or is there a spring? Are those in your system? No. So no potential energy. No real kinetic energy. Okay, at least not on the macroscopic scale, because if you're talking about the motion of the water molecules, that counts as microscopic. Okay.
Turning
It's a
it.
strong term. Like,
Yeah, like just bear with me here. Okay. So we have work and we have change in thermal energy. Here's another situation. Maybe this one's more believable. Okay. So do we have a change in kinetic energy inside this pot? No, right? Do we have a change in potential energy? No, we're not dropping it or putting springs on it or anything. So no change. Do we have any external work happening on our system? No, remember, work has to have some sort of displacement. Is anything being displaced? No, right? Because what would the force be? They're the force of fire. And if there's a force, even if the fire had a force, it would have to like shoot the pot up into the air for it to be considered mechanical work. It's okay, fine. It's an inductive heating. But shut up. But the total energy increases, right? You can measure there's a temperature change. So what are we missing? Well, probably heat.
An equation.
An equation.
She's like, you're right. But we're
That's
not
always
right.
true. We're missing some math. So remember, here's some definitions. Thermal energy is the energy of a system due to the energy of the molecules and atoms inside. So if the molecules and atoms are moving around or jiggling or whatever, that's your thermal energy. Okay? Temperature measures the thermal energy. So there's some relationship between temperature and thermal energy, but if this goes up in about the same amount. Okay? Heat is energy transferred between two objects which are at different temperatures. So if you touch the table, there's a heat transfer, and that's Q. Okay? So in terms of the kettle, when you put fire on something, that is transferring heat from the burning wood to the kettle. Okay? And it turns out there's signs for this. So if your heat's going into the system, we call that positive. So the Q for the kettle would be positive. Okay? Heat going out of the system, we call negative. So if you had, let's say you put the kettle in the freezer afterwards, then the system would have negative Q. Okay? So here, let's try that out. We're going to do this until we get 100%. Although in this class it might be easier. The other class never really got there. Never get to eat lunch. Just eating. Lots of calories.
I want to see the lab that lit that shit on fire.
We could do that.
I know, that's what I'm saying. Some dude with a lamp.
I don't know if I have time to build one.
Right?
We just calculate all the food we eat. We'll burn a steak.
I don't even know how you did it. What do you do? I like shit on fire for a living.
That's awesome.
Right? It's just lit.
All right, so it's either plus or minus. All right, please discuss quickly and we'll vote again.
He's leaving.
Minus.
Well, I mean, no, it's getting colder, but when are you going into negative?
You're missing two people.
Right? So Q is only the heat, is the energy transfer. Is it like losing? Is the energy losing out of the code?
Okay,
Or is it absorbing both?
we lost somebody. But okay, we have 100%, but not 100% response. But that's okay. So, what's your system?
The Coke.
Coke, right? Including the bottle. Okay? So if you put a warm Coke in the freezer, which way does the heat go? Out. Out. So your system is the Coke. What's your environment? Freezer, fridge, yeah. So if your heat is going from inside the Coke, inside the system, to outside of the system, into the environment, then your Q should be negative. Okay? Heat is leaving the system.
If you said that the system is the freezer, is that the next question? If you
No.
said the freezer is the Coke. Like, it's the freezer and the Coke. Would Q be zero because it's leaving?
Q would be 0. Yeah. If the system was the freezer and the Coke, and no heat left the freezer, entered the freezer, then Q would be 0. Yeah. So it depends on where you put your boundaries for the system. Yeah. Here's. We'll just do like. You're getting more candy. Good choice. I was gonna bring more candy, but so trick-or-treaters literally ate every piece of candy that I bought.
I guess if you got
Because you live in Point Loma. If you live where I'm at,
looking
you have all your candy.
Yeah, I live in like the most Halloween-friendly neighborhood maybe on the face of the earth. We had 1,000-something trick-or-treaters.
Wow.
Like I bought 2,000 pieces of candy at least, and they were gone.
And you
And
just
we-
want candy. It's like,
I didn't start out stingy enough.
Oh.
I was giving like,
Handful.
they're the little cute kids come first. You give them like a couple. Anyway,
I had this with somebody else.
all right. So, yeah, and somebody's gonna be like, we didn't really define the system, but if your system is the Coke, okay, then the heat is moving from the environment into the Coke, and then Q should be positive. Here's a last question.
In your room temperature room.
Not really. Just like a really easy question.
Somebody might still get it wrong.
Yeah, I'm sure they will. Someone always gets it wrong.
That's the second. There's always someone. I can do that kind of stuff.
I know. Easy.
Waiting on one person.
Who's the
All right, you have 2 more seconds.
Come on, guys, you gotta vote.
I'm not waiting anymore. That's not even an answer. All right. Well, it's 0. All right.
The sound of defeat. Well, it's
Okay.
Dude, that's
Who has that number 3? I'm not here.
That's awesome.
Dude, number 3.
I mean, number 2 looks like a
That's
toilet in
fancy.
county.
Great
That sounds
toilet
cool,
seat.
bro.
Okay. Remember,
Caca particle.
we answered this first
Minus the
question
lid.
quietly to ourselves.
That's true. It's a jail. It's a jail toilet.
Because it fucking is number 1, is that porcelain or plastic?
Doesn't matter.
It looks plastic.
It does.
It's either plastic or painted wood. So take it back to number 2. It's a complicated question.
All right. Okay. Let's discuss this. The heated seats,
Oh yeah.
like the bidet.
No.
No, I haven't tried
It is
that.
not a heated seat.
Well, they have those like fancy Japanese toilets with like the heated seat and the bidet.
Heated up.
I was traveling with one of like we were traveling with like another couple in Italy, and every place we stayed had a bidet. And like one of the other guys we were with was like, he's like, "What is this for? Like, just use toilet paper." And
Obviously you wanted
he
to.
was having some issues because we were eating a lot of cheese. And then he came out one day and he's like, "Guys, the bidet is magic."
So, we went to
Like,
the
that one's gonna heat up.
and we had an artistic
I know
and
it's
we
different.
walked in and he goes, guys, there's a water fountain in the bathroom.
I mean, I could be wrong. I could be dead wrong.
He's like splashing it. I'm like, I don't want to do that. He's like, why?
Yeah, I
I'm
could
not
be dead
doing
wrong.
it.
It's not drinking water.
Don't touch that.
Oh, I'm the only one.
So the correct answer is C.
Yeah, I did it.
Room
No, they're all
temperature.
the same.
Okay, it's 71 degrees in here. I didn't ask like which looks most delightful. In that case, this one looks delightful, but it's gross.
I just like the vision of walking into a bathroom and seeing 3 toilets on 3 different kind of like tiles.
Okay.
Like, just
You guys got way out in the weeds on this one. If it's 62 degrees in this bathroom, what's the temperature of this toilet? 62. 62. 62, yes.
Wouldn't the material matter though?
It does. Not for temperature. Okay? So.
Oh.
Sorry, I don't know. That's just the tour. I found that picture when I Googled this. So heat transfer, which is heat, Q, not temperature, is what you feel. Okay? We know all of the things in this room, except for the other people, are 71 degrees. But some things feel colder when you touch them. Why? Why does metal feel colder? Yeah, it transfers heat quickly. Okay, it's a good conductor. So conductors feel colder because they're basically sucking energy out of you faster. Okay? So conductors feel colder, even if they're not a different temperature. We don't feel temperature. We feel heat. Okay? Also, heat transfer, not temperature, is what burns you. You can touch something that's really, really cold as long as it doesn't transfer heat or cold quickly. Okay? That's why you can get burned by something cold and something hot. You get burned by cold things because a lot of energy leaves your body. You get burned by hot things because energy goes into your body quickly. Okay? You can touch something really hot. If it doesn't transfer the heat to you, it's not going to burn you. All right? Which is why they let kids use these sparklers. They get really, really hot, but they have really poor heat transfer. I mean, you can still burn yourself, but it's not that.
It's more like that where it's like saw a video on Netflix where like this guy takes his hand in water and he touches a super hot pan.
Oh. Yeah. If you have, that's why you can touch things with an insulator, right? If you have an oven mitt on, you can touch something really, really hot and not burn yourself because it slows down the heat transfer so much that it doesn't actually get to you and to burn you. It'll warm up, but it doesn't transfer heat fast enough to burn you. Fun fact, when I was in grad school, I was dating this guy that worked at the super low temperature lab, which is super awesome. So they had liquid nitrogen, and they also had liquid helium, but you don't want to mess with that shit. So you can put liquid nitrogen in your hand, but what do you think you have to do so you don't burn yourself? Keep it moving. You bounce it, right? So we're all sitting there bouncing liquid nitrogen because, like, we're cool. And we're, like, playing with the liquid nitrogen. And one of the postdocs comes up and she's like, oh, I want to play. And they poured liquid nitrogen in her hand and she just stared at it and burned all the skin off of her hand. And we're like, fucking theoretical physicists, man.
We were like in fifth grade and we were doing like kind of like this. We got that dry ice and you put it in a glove.
Oh, yeah.
And because you tie it off and the gas is there.
Oh, yeah.
And when he was fucking holding it like this and it burned through the glove into his hand and he like freaked out and it wouldn't like leave his hand.
Yeah.
Melted there, like, yeah, you're fine. Like, you go home.
Yeah, the main disappointing thing about this was this person had a PhD in physics and still burned themselves on liquid nitrogen. Turns out smart and smart are different. SMRT. Okay, so anyway, here's our equation from before. Here's our thermal energy, change in kinetic energy, change in potential energy. We don't worry about so much when we're talking about thermodynamics. Here's work done on the system by the environment, so any external forces coming in. But we have to add one more thing, and it's heat. Okay, this is heat transferred into the system. All right, and if it gets transferred out, what do you do with this? Negative Q. Okay? So once we get rid of those things, we call this the first law of thermodynamics, which is not, don't tell people about thermodynamics. It's just this. So the first law of thermodynamics is thermal energy is heat plus work. Okay? So work done on the system by the environment, heat transferred into the system, and change in thermal energy. This is the first law of thermodynamics. All right? You guys want to go home? And this is our first law of thermodynamics. Okay? That's the first law. And that's where we left off. Did we do this slide? Have we done this one? We did this one? Okay. So let's move forward to heat transfer and temperature change. Okay? So if we're doing heat transfer and temperature change, we're not using any external work, right? We're not applying any physical forces to our thing, just microscopic stuff. And perhaps you've seen this. Anyone? This look familiar? Yeah, this looks like chemistry. That's okay. It turns out that chemistry is just applied physics, so whatever. Temperature change, heat transfer. What's this M? Mass, okay. And then what's C? Specific heat. Okay, so specific heat tells you about how much energy it takes to raise 1 kilogram by 1 degree Kelvin. Okay, so how much heat do you have to put in to raise the temperature 1 degree for a certain amount of a substance? All right, and here's some standard C's, right? These are specific heats. So we have aluminum, copper, gold, lead, ice, and then for some liquids we have alcohol, mercury, and water. Okay. Now, what does it mean if something has a really low specific heat? So, like, which one of those things would make a really good frying pan? Do you want the number to be higher or lower? Lower, right? Why? Yeah, it heats up faster because it takes less energy to change the temperature. Okay? So it takes less energy to change the temperature 1 degree. So what's most of our cookware made out of? What are your pots and pans made out of? Aluminum, okay? Copper. Kat, if you have like a skillet, right? Like a cast iron, that's iron, right? So people always that like to cook rave about cast iron skillets. So if you read stupid food blogs, why you can see that gold and lead have much lower heat capacities. Why do we not make cookware out of, let's say, gold? Well, lead is poison, so that's why we don't use lead. And gold is too expensive. Also, it's not very durable. Like if you make your cookware out of solid gold and you like drop it, it's going to dent. It's very soft, okay? So you probably have it would be nice you have little flecks of gold in your food because the gold doesn't stay together that well, but not really a cost-effective way to do things. Now, if you have the means, copper and iron are pretty good, but aluminum works too, okay? The professional says no. Okay, apparently you're all cooking wrong. So yeah, that's what specific heat is. All right, that tells you how much energy you need to change something's temperature. All right, so we're gonna do this quick and really easy example. Aluminum. So how much heat is required to raise the temperature of 3 kilograms of aluminum from 20 degrees to 30 degrees Celsius? Equal to MC. So we use this formula, Q is equal to MC delta T. And we just want to find Q. So what's our mass? And we just want to find Q. So what's our mass? We're given our specific heat of aluminum, it's 900. We're given our specific heat of aluminum, it's 900 kilograms joules. And then we have kilograms 20 to 30 degrees. So what is delta T? And then we have 20 to 30 degrees. So what is delta T? So here's 10. The thing. Does it matter if we convert if we're subtracting? So here's the thing. Does it matter if you convert if we're subtracting? If you do 30 minus 20, you get 10 degrees. If you do 30 minus 20, you get 10 degrees. That's 200. Okay. Let's say we convert this to Kelvin. Kelvin. That's 200 and 393 Kelvin. Minus 293 Kelvin. Also 10. 303. So if you're subtracting temperatures, you don't actually have to convert to Kelvin. So if you're subtracting temperatures, 10 degrees you don't actually have to convert to Kelvin. The same difference. Okay. 10 degrees Celsius as 10 degrees Kelvin if you have a difference in temperature. Literally, as 10 degrees Kelvin if you have a difference in temperature, just one temperature and not taking a difference in temperature, like just plugging in temperature to one temperature and not taking a difference in temperature. So if it's just really if an equation has T in it, okay, so if it's just if an equation has T in it, Kelvin or Celsius, use Kelvin. If it has delta T in it, Kelvin or Celsius are fine. Okay, 10 Kelvin. So, and why do I write it in Kelvin if I did 10 Kelvin? And why do I write it in Kelvin if I did cancel it, right? So if you look at the units here, we know it's the same. This thing looks like it has dumb units, but it's because they have to cancel. This thing looks like it has dumb units, but it's because they have to cancel to give us joules. Okay? And so that's going to give us about 27,000. And so that's going to give us about 27,000 kilojoules. So 27 kilojoules. This is the plug-in formula, but I want to do this kind of problem because I want you to see how the units work. But I just want to do this kind of problem because I want you to see how the units work. All right. And how to deal with temperature. Q equals MC delta T. Okay. Here's another thing I want you to think about. All right. Oh, Q equals MC delta T. Here's another thing I want you to think about. If we don't have any external work, what is this also equal to? If we don't have any external work, what is this also equal to? Thermal energy, right? And remember I told you thermal energy is proportional to delta T. Right? And remember I told you thermal energy is proportional to delta T. So this is also equal first law of thermodynamics. Thermal energy because of that means thermal energy is proportional to T. Okay. That means thermal energy is proportional to T. What's this? If you graft it, what would that be? It's a constant slope because remember M is constant. Okay. And it's a constant slope because remember M and C is a constant.
just how much of the substance you have.
So that's what I mean when I say these two
is a
things are
constant.
linearly related. You can
So
also
that's what I mean when I
get
say
the
these two
literal
things are
relationship
linearly
between them.
related.
You can also
Okay.
get the literal relationship between them. Okay. As a side note, there's also molar heat capacity, and really this matters if you can rewrite this equation so that you get the same thing, but you use moles, which is sometimes useful if things are small. Okay, so you can convert this back and forth between moles or mass. We're not going to use moles very much here, but I just want you to know that you can do that because I think that's how it shows up in chemistry. I don't know. It's been a long time since I took chemistry. So yeah, it turns out this is the molar mass. This is just a side note. You don't have to know this for a test or anything. This is the mass. This is the number of moles. You multiply those together, you get the actual mass. Okay, and there's these tables for molar heat capacity. And so, but what we are going to see later is we have something that looks like this, which is Q is equal to NC delta T. When we start talking about gases and we do like PV equals nRT stuff, sometimes we're given moles, and then you just need the molar heat capacity, or you have to convert to mass. Okay, and so depending on like what we're doing, these two equations are equivalent, but they have different applications. Okay, and these are just, this is the specific heat, this is the molar mass, this is the molar heat capacity. It's easy to go back and forth. It's just two ways of doing the same thing. All right, and here's where it's going to come in later. You will see these things again. So what? Well, this is called a PV diagram. Okay, this, what's the P stand for? Pressure. What's the V stand for? Volume. And then you have these temperature lines. These are called isotherms. That means it's a line of constant temperature. Okay, how would you find a line of constant pressure? What would it look like? Yeah, horizontal, right? Anything along this line has pressure P1. All right, the volume's changing, the temperature's changing, but the pressure's not changing. Okay, any vertical lines, these are constant volume lines because anything along this line has volume V1. Anything along this line has volume V2. Okay, so you can have constant pressure, constant volume. You can also have constant temperature. That's a little more difficult because you have to know where these lines are. But if you follow one of these lines, if this is 10 Kelvin, and this is 10 Kelvin, and this is 10 Kelvin, and this is 10 Kelvin, anywhere along the line you have the same temperature. Okay? So we're going to later deal a lot with PV diagrams, and we'll draw these little charts. So these are states. Okay? And what I mean by a state is a state has a particular pressure, volume, and temperature. Okay? And you can change states, and the way you get to a state matters because you can go through this process to get to this one, or you can go. So basically, let's say this is 50 Kelvin and this is 100 Kelvin. All right, so you can change temperature. Both of these have a temperature difference of what? 50 Kelvin. Okay, so if you go this way, your temperature change is 50 Kelvin, and if you go this way, your temperature change is also 50 Kelvin. Okay, but you've gone a different path. One way, you've gone the same temperature change, but you kept the same volume. The other way, you have the same temperature change, but you didn't change the pressure. Okay, so one of them, you're either you're adding more pressure. So like, let's say you put this in some sort of pressure cooker, but you kept the volume constant. Okay, in this case, you've kept the pressure constant, right, but you've changed the volume. Okay, there's different ways we can go about this. We'll talk about this in more detail later. But the end result is you have the same delta T. Turns out these things give you different amounts of heat. Okay, the process you use matters when you're talking about gases. So we have two different types of heat capacity, one for constant volume and one for constant pressure. Okay, and these we'll talk about in more detail later, but I just want to mention them while we're talking about the standard Q equals MC delta T. Okay, and the nice thing about the Q equals MC delta T is it's generally true for solids, liquids, and gases. This is something that really only comes up when you get to the gas state, and it's only really true for an ideal gas. Okay, and we'll talk more about what that means later. So anyway, we're going to talk about calorimetry and phase change. For some of you, this will be a review, so we'll go through it sort of quickly. What are the phases of matter? You can read them. Yes, solid, liquid, and gas. Those are our phases of matter. And solids have a definite shape, definite volume. Molecules don't really move. What can molecules in a solid do? It's kind of like jiggle. Okay, that's all they can do. Liquids have a definite shape, but it's the shape of whatever container they're in for the most part. They have a definite volume because they don't really expand and contract easily. And the molecules are held together, but they're more loosely bound. So they have lighter bonds between them than a solid, okay? A gas, molecules move about freely. Now in physics, both of these things are considered a fluid, but there's a pretty big distinction between how a gas behaves in thermodynamics and how a liquid behaves, okay? So let's talk about what happens with heat transfer. So let's say we have a temperature versus heat graph, okay? So let's start with, I don't know, something like simple. Let's start with water, okay? So let's start with solid water. As we add heat to the water, what happens to the temperature of the water? It rises, okay? And what should the slope of this be, or what should it have to do with? MC, yeah. Well, in this case, it would be 1 over MC because heat is on the x-axis, but it's related to this. Remember? This has to do with our slope because we're relating this and this, and we know they're linear. Does that look linear? Okay. Now let's say we get to the melting point. Right? When it melts, yeah, it stays constant. Okay? Which means we're still putting heat in, we're still putting energy into the system, but what's happening to the temperature? It stays the same. Okay? Which means that does this equation work for this? No. Because if you look at this, delta T is always going to be what? 0. Okay? So this is a temperature change, this is a phase change. Q is different for phase changes. And then, of course, this becomes a liquid, right? Until you get to the boiling point. And then you have another phase change. And then it becomes a gas, and you can heat up the gas. Okay? What this says is, like you, I assume, have had a glass of water with ice in it. Yes? Once the ice, at the point where the ice starts to melt, the water and ice end up being about the same temperature over time. That's your zeroth law, right? You have thermal equilibrium. But you can have water and ice both at 0 degrees, okay? If you go above 0 degrees, then everything becomes water. If you go below 0 degrees, everything becomes ice. But you need a certain amount of energy to do that phase change, okay? And here's your slope. So it turns out the phase change is given by this formula. So the heat it takes to change phase is this. And this is just m, which is the mass, times a constant that has to do with the material. All right, and all these constants will be given on a test, but I just want you to know which ones are which. This is the latent heat of fusion. What does that have to do with? Which phase change? Liquid to solid, solid to gas, liquid to gas, solid to liquid, or liquid to solid, back or forth. How do you know if you're going one way or the other? The sign, okay? Because remember, when is heat positive? Going into the system. When is heat negative? Coming out of the system. So if you have ice and it's turning into water, should this be positive or negative? Positive, because to get ice to turn into water, you have to add heat. Heat goes into the system, so Q is positive. If you have water that's turning into ice, negative. Okay, you have to pull heat out of the system in order for it to freeze. All right, this one's called the latent heat of vaporization. So that's liquid to gas and gas to liquid, depending on the sign. Okay, if you have a liquid and you want it to be a gas, is Q positive or negative? Liquid to gas.
Positive.
Positive, right? If you have water and you want it to be steam, you have to add heat, okay? If you have steam and you want it to be water, you take it away. That's condensation, okay? So, yeah. Anyway, that's that. So we have two ways of figuring out heat, right? We have temperature change, but we also have phase change, all right? And here's a fun chart that you don't need to memorize, but it's always nice to have as a reference for different materials. This includes their melting point, the latent heat of fusion, boiling point, heat of vaporization, okay? So you know that these phase changes only happen at these temperatures, okay? Because if you have water, let's say you have, well, let's do it. Let's say you have water at negative 20 degrees. What do you have to do before you get to a phase change? Or sorry, ice. You're right, ice. How do we get the ice to a point where we can melt it? Heat it up. To what temperature? 0 degrees. Okay, so let's walk through this. Okay, and this is this is the kind of stuff you can expect to be given to you. Okay, so you don't need to memorize a bunch of constants, but you do need to know how to use them. Okay, if I give you the chart, know how to use it to do the problem. So here we want to know how much heat is required to change 200 milliliters of ice at negative 20 degrees Celsius, which is apparently a typical freezer temperature, into steam. Okay? So what's the first problem you see with this?
Gas.
So before we even do MC delta T, which is the first thing we have to do to get to a point where we can melt it, what's M? Yeah, milliliters is a volume. Okay, so you can't use that as M. How do you get from, yes? Yes, you have to use the density. Okay, because remember, volume mass density is mass over volume. We were given volume, so we need to do this. Volume is, we need mass, sorry. Mass is rho times volume. Okay, and just fun fact, a milliliter, so we have our density in kilograms per meter cubed. So this is 920 kilograms per meter cubed for ice. How do we get the volume in meters cubed? So milliliter it converts to centimeters cubed, right? 1 to 1 if it's water. Close enough for ice. So this is 200 centimeters cubed. But we need it to be meters cubed. This is in cubic centimeters. How many cubic centimeters are in a cubic meter? Do not say 100. How many centimeters cubed are in a meter cubed? Yeah, 1,000,000. Okay, do you want to know why? So if you just have one-dimensional things, like a length, okay, 100 centimeters is equal to 1 meter. Okay, if you want cubic centimeters and cubic meters, you cube stuff. Now that's no problem for this one thing. That's 1 meter cubed. But this becomes 100 cubed centimeters cubed. Okay, so this is 1 times 10 to the 6th centimeters cubed is equal to 1 meter cubed. Okay, when you're dealing with volume, it's cubed. Not just the units, but the values next to the units. Okay? So 1 meter cubed has 1,000,000 centimeters cubed in it. Okay? 1 meter has 100 centimeters in it. But 1 meter cubed has 1,000,000 centimeters cubed in it. And people fuck this up all the time. Do not let that be you. Okay? Alright, which is the only reason I put this in this problem, because I want you to see it before a test. Okay? Because it's just such an easy conversion if you know what you're doing. Alright? So, this becomes how many centimeters? So, 1 meter cubed over 1 times 10 to the 6th centimeters cubed. Okay? And so when you actually do this out, you get something like 0.184 kilograms. Okay? And now we have our mass and we can begin. the actual problem. All right. So we're going to have several stages. So if we start with ice and it's at negative 20 degrees, first we have to warm it to 0. That takes an amount of heat. That's a temperature change. Then what? Then what do? We add more heat to melt the ice, right? So we raise the temperature, then we melt the ice. So we have an MC delta T, and then we have an ML, okay? And then you have water. But does water just boil when it's at 0 degrees? Nope. You use MC delta T again. You heat it to 100 degrees. And then you have to use another ML to get it to change phase from water to steam. So there should be 4 Qs, and the total heat you need is the sum of all 4 Qs. So Q1 is M ice, C ice, delta T, okay, which is 0.184 kilograms. The specific heat of ice is 2090 joules per kilogram Kelvin. And the change in temperature final should be what? 0 minus negative 20. So that's 20 Kelvin. Okay, so 0 minus negative 20, positive 20. Which makes sense because you're heating up ice, which means you're putting heat in, and Q should be positive. Okay, so that's going to give us 7.7700. That's 8,000. So 7.7 kilojoules. That's about 7,700 joules, or 7,700 joules. Okay, so not a ton of heat. Q2. Now we have ice that's 0 degrees. We need it to be water. So we use mass. And which latent heat? Fusion or vaporization? Fusion. We're going from a solid to a liquid. Is it positive or negative? Positive, we're putting heat in to melt the ice. Okay? So we have the same mass, 0.184 kilograms. And why do you think it's mass? Do ice and water have the same volume? No, right? The density changes as you go from ice to water. But you know what doesn't change? The mass. Okay, because the amount of molecules is still the same, they're just structured differently. Okay, and mass comes from the individual atoms. So, then we use the latent heat of fusion. That's going to be 3.33 times 10 to the 5th joules per kilogram. Okay, which means the second heat, the heat we need to melt the ice, that's going to be 61.3 kilojoules. All right, so heat ice, melt ice. Then we want to heat the water. Okay, so once again we use MC water, delta T. Okay, so still 0.184 kilograms, the mass hasn't changed. But now we use the specific heat of water because we're dealing with water. And the specific heat of water is much higher than the specific heat of ice. It's 4190 joules per kilogram Kelvin. What's our temperature change? Well, we started at 0. What do we need to get to? 100. So 100 degrees. Okay, we need to heat it up 100 degrees. All right, so you multiply those together, you get something big, like 77. Okay, so we've used this. So far we're at about 150 kilojoules, give or take. And then the last thing we need to do need to make water into steam. Okay, so that's a phase change, and that's the latent heat of vaporization. All right, it's positive because we're adding heat still. So the mass is still the same. The latent heat of vaporization should be 22.6. And that gives us something giant. Apparently you need a lot of energy to make steam. 415.8 kilojoules. Okay, that's times 10 to the 3. Right, so and this is in thousands. And then if we want the total Q, Q1 plus Q2 plus Q3 plus Q4. So about 150 plus 415, that should be about 560, 575, 562. So that's the amount of energy you need to take very cold freezer ice and turn it into steam. Now why you want to do that, I'm not sure. You could just start with water at room temperature, but here you go. Although it turns out most of the energy comes from what? What step? Yeah, vaporization, right? The last step is the most energy costly. So actually, boiling water from ice is not that much more energy costly than just boiling room temperature water, because most of the energy just comes from here. Going from hot water to steam, it's a big jump. You need a lot of energy, which is why it takes so long to make tea. Sort of. Okay. All right, here's a question. All right. Mostly think B, although there's some strong holdouts for sticky. Please discuss and vote again. Just like that phrase. It's always bad when your joke answer gets lots of votes. That would be funny. All right, another couple seconds. Make sure you voted again. Lost people already. Better. Was that just you? So there's more energy, right? Because you can see the difference in energy between very hot water at boiling and steam just after boiling. It's about 415 kilojoules. Okay, it takes a lot of energy to make steam, and that energy gets stored in the steam. All right, it's released if you take the steam back to water, and it's released on you as the water condenses on you. Okay, so all of that energy comes out as you put your hand in steam. So it's actually much worse to get burned by steam than it is to get burned by water, which led someone in the last class to ask, is that why people always scream in movies when somebody breaks a pipe and it sprays steam at them? And I guess the answer is yes, but that's not real. Okay. So anyway, the application for this is something called calorimetry, which is just a fancy way of saying conservation of energy for systems in thermal contact. Okay? Basically, if you have system A and system B and you put them in thermal contact, which basically just means touching, okay? And it's a fancy way of saying touching. Heat flows back and forth between the systems, and you could say QA, QB. Eventually, what do we reach? Thermal equilibrium. Everything is the same temperature at the end. I'll get to in a second. And what that means is any heat that goes from here to here, the negative version of that heat goes the other way. And when you sum up all the heats going back and forth, they should be 0. And that's conservation of energy still, okay? So blah, blah, all that jazz. And that's the end result. And it turns out you just need these things. So we basically only did one side of that equation. We only did one direction, right? If you wanted to talk about what was actually heating that stuff up, you'd say, like, we threw this in a big pot of water or something, or we threw a metal bar in there that actually melted the ice, okay? So it has to be two systems. This is just one isolated system. This is what happens when you have two systems in contact. Yes?
What is dry ice?
What is dry ice?
Yeah.
That's carbon dioxide. Oh, that's sublime. And you can get, I think that's still called the latent heat of vaporization. But it burns, yes. Yes, it does burn because it transfers heat out of you into the ice. That would be systems in thermal contact. One system is you, the other system is the dry ice, and they transfer equally, but it hurts. What? Well, ice and salt. What does the salt do? Yeah, it increases the temperature you need. Like, so it changes the freezing point of ice. Yeah, so you can make things colder. So, like for instance, why do we sprinkle? Well, we don't do that here. But let's say we lived someplace where it actually got cold. Like Michigan, that's a good choice. Why would you put ice on the sidewalk when it's ice? Why would you put salt on the sidewalk if it's icy? Yes.
It makes it more difficult for the water to form ice.
Yeah, it makes it more difficult for the water to freeze, right? And if the water doesn't freeze, then you don't have ice that you slip on and fall and either look stupid or actually hurt yourself. Okay. All right. Which are both good options. Do you guys want to do one of these problems? They're pretty easy. Okay guys, so this is a calorimetry problem, meaning we now, instead of having one system that we're calculating the heat in or out, we're calculating two different systems. And what are our two different systems in this case? Well, they're going to be ice and steam. All right, and the key to calorimetry is that when we add up all the heat that goes into the ice and all the heat that comes out of the steam and we add them together, we're going to get 0 because any heat that comes out of the steam must go into the ice because calorimetry just means basically it's trapped in a thermos, so anything that comes out of one thing has to go into the other thing because there's literally nowhere else for it to go. Now the key here is we want to find T final. So when it reaches equilibrium, we want to know what that equilibrium temperature is. In this case, we have, here's our two systems, right? We have 3.5 kilograms of ice at 0 degrees Celsius, and then we have 1 kilogram of steam at 100 degrees centigrade. Sorry. And of course, we might need to think about things in terms of Kelvin. So, oh no, but it's a difference. So we don't have to convert the degrees. So what we're going to do is we're going to calculate the heat transferred into the ice and the heat transferred out of the steam. What do you think we're going to get at the end? Well, unless your ice is a lot of ice that's really, really cold, or your steam is like an unbelievable amount of steam that's really, really hot, neither of which seems to be true since they're about the same amount, we're probably going to end up with water. And the like key here is what temperature is the water going to be. So first, we're going to figure out all the heat from the ice plus all the heat from the steam. And we know this has to equal 0, and we're going to solve for T final. All right, so here's this. This is all the stuff for Q for the steam, and this is all the stuff for Q for the ice. So for Q ice, we want heat transferred probably another R there, into ice, right? Because the ice isn't getting colder, so that means heat has to be going into it. Now Q ice is going to be equal to, there's first a phase transition, so the ice has to become water. So that's going to be M for the ice, times latent heat of fusion, because we're going from a solid to a liquid. And this will be positive since we're going from solid to liquid. That means you're adding heat into it. And then M ice, the melted ice has the same mass as the ice, so we can leave it like that. C water, and then T final minus T initial, that's our delta T. But remember, we're trying to solve for T final, so we want to write it like this. So this is just our stuff for ice, like this. Okay, we can plug in some numbers and it gives us something that looks like 3.5 kilograms times 3.33 times 10 to the 5th joules per kilogram plus 3.5 kilograms, 4190, this is C for ice, joules per kilogram Kelvin, T final minus 0 degrees Celsius. And we're going to leave this like this for now, and you'll see why. I'll come back to it. Then we're going to talk about the steam. So heat transferred out of steam. So that's going to be Q steam, which is we're going to have to go from steam to water, and then we're going to cool down the water. So this is going to be M steam, L vaporization, because remember, we're taking the heat from the steam out and giving it to the ice. So that's where the negative sign comes from. And then this is our first Q, right, just for steam. And then we have this other term where we're actually cooling down the water. So this is going to be M steam still, C H2O again, water, and then delta T, so this is going to be T final minus T initial, which in this case is 100 degrees Celsius. So we can plug in some numbers. We end up with -1 kilogram times 22.6 times 10 to the 5th joules per kilogram. And then this is going to be plus 1 kilogram, 4190 joules per kilogram Kelvin. And then T final minus 100 Kelvin. You're going to be like, why isn't that negative? But whatever T final is, we know it's going to be less than 100 because this can't get hotter without turning into steam. Okay, so this is our heat transferred out of the steam. And then we go back up to this idea. So we add all these together. So Q ice plus Q steam equals 0. And this just ends up being sort of an algebraic nightmare. But you just put these together, set them equal to 0. Okay, so 3.5 kilograms times 3.33 times 10 to the 5th plus 4190 T final plus (1 kilogram negative 22.6 times 10 to the 5th plus 4190 T final minus 100 equals 0. Algebra happens. And you should get your T final when you solve for T final, right? So here's your T final. You're going to distribute here and solve over here. you just do a bunch of algebra, which I'm not going to do right here, and T-final is going to give you something like 78.8 Celsius. Okay, you can also get this in Kelvin, but that's what you're going to end up with. So let's talk about heat transfer. This part's kind of fun. This is just heat transfer mechanisms and how they're used to cook things, I guess. Conduction. Conduction is just basically fire heats up pan heats up food. We'll talk about what happens on the microscopic level in a minute. Convection, fire heats up air, right? Air rises when it's hot and then replaces the cool air falls, and then that creates something that looks like this. Oh, yeah, there it goes, like that. And then radiation, okay? Electromagnetic radiation, although technically all of these are radiation. What kind of radiation is this? Infrared. So you know that whole electromagnetic spectrum thing, right? What do we see? Colors, yes, visible light. Okay, so visible light, that's the middle of the spectrum. If you go in the violet direction, right, you get ultraviolet, and then you get X-rays, and then you get gamma rays. Okay, if you go in the other direction, you get to red, and then you get infrared, and then you get radio waves, and then you get microwaves. I think it's that order. But those are longer wavelengths, lower energy. If you go this way, it's shorter wavelengths, higher energy. Okay, and which ones are dangerous?
Gamma.
Gamma's pretty dangerous, yeah. Where's the cutoff? So when people are like, radiation is scary, they don't know they're not being specific enough. Okay, because there is some radiation you should avoid. Like, for instance, why do you wear sunscreen? UV is not great. Okay, UV, X-rays, gamma, you want to limit your exposure to those. Why? What's special about that energy cutoff? What does it do? No, microwaves can cook you. You just want to get hotter. Well, yeah, it's dangerous to be in a microwave, but it's not really dangerous to be near a microwave. Well, why do you think that radiation is dangerous? Like, what does it do?
I mean, there's different things that radiation does, like, it
Messes up your atoms. How? So it turns out anything UV and above is called ionizing radiation. What does ionizing mean? Yeah, it rips up an atom, basically. It takes apart, either it takes a positive charge off or it takes a negative charge off of an atom, making it an ion. Most atoms and molecules are electrically neutral, meaning they have the same number of positive charges as negative charges, so they don't really interact with things around them because they don't have a lot of mass, so they can either bump into things, but there's a lot of space between atoms, so, they don't do a whole lot. If you have an ion, it's positively or negatively charged. And when we do Physics 200, you'll see the forces of charge are much, much bigger than the forces we deal with from gravity and other things, okay? And charge is the most common force. So if you ionize, usually water, okay, all of those things ionize water, and we're made of a lot of water. Just charged water molecules floating around, not that big of a deal. But when the water molecules come into contact with other atoms, now they're going to interact with them. So if one of those water molecules comes in contact with some of your DNA while your cells are replicating, or whatever it is that cells do, because I don't know much about biology, they can rip apart pieces of your DNA. And sometimes that's not that big of a deal. Either you have some RNA or whatever that stuff is that fixes it, or the cell just dies. But once in a while, it screws up the replication process in such a way that the cells don't know when to stop making more cells. And guess what we call that? Cancer. Okay? And the more times you ionize the water in your body, and that might interact with the DNA, the higher the probability that you'll get some sort of cancer, because it's just a roulette game. And there's enough players in that game that the statistics are nice and linear. So more radiation exposure in the ionizing range, right? The chances of cancer go up linearly, which is, I guess, nice because you at least know what your risks are. But, you know, microwaves are not going to do that to you, okay? Visible light is not going to do that to you. Get into UV, the reason it's dangerous is because there's an actual biological pathway that makes it dangerous. Anybody that says, like, using your cell phone is going to give you a brain tumor, they don't actually have any evidence that that's true. I mean, at most, it might slightly warm up your brain a little bit, but not that much. And so there's not really any good data that says that, like, microwave and radio waves hurt you. And we've had radio waves and microwaves floating around for a long-ass time now, and it's not, we have a lot of evidence if there was something going on. But we're 100% sure that ionizing radiation can hurt you, okay? And we have lots of evidence that it does. And just for scale, right, when you're going for, this is why, like, going and getting a CT scan for funsies is a bad idea, okay? When should you get a CT scan? When should you get an X-ray done? When you need it. When the consequences of not doing it are more dire than the risk of doing it, okay? So make those decisions wisely. Turns out MRI doesn't seem to have a lot of long-term risks. So if somebody wants to give you an MRI for fun, sure. But no X-rays for fun, which is great, because when they invented the X-rays, people would just, like, take X-rays of themselves for fun all the time, and they used way more dose than they needed because they didn't know what they were doing, and lots of people got all kinds of fun cancers for fun. You know the Curies, right? So we're going way off topic now. So Madame Curie, big deal. She's a lady that did physics, and she won 2 Nobel Prizes, blah, blah, blah. Okay. Everybody's like, yay, Madame Curie. She had a husband named Pierre, also a smart guy. And they discovered radium together. Mostly she did, but he knew about it too. And so he would, like, walk around with radium in his pocket, and they, like, handled it with their hands. Like, they're just, like, picking up radioactive stuff and being like, how cool is this? But to be fair to them, this was the first radioactive stuff anybody had really dealt with, so nobody knew that it was dangerous. They were like, it's glowing, how fun, rub it on your face. So guess what killed Pierre Curie? No, he got hit by a truck. But it was probably because he had severe bone cancer at the time and was moving very slowly and couldn't see very well, because he was just, like, we didn't have the diagnosis back then, but he was probably riddled with cancer by the time he got hit by the truck. Maybe that was more of a godsend. Anyway, but it's a fun punchline, right? Okay, so conduction, all right? Temperature difference causes thermal energy to flow from hot to cold. This is when you're dealing pretty much with solids, okay? So like a metal pan, for instance. And here's a beautiful animation. Here is your source of heat. And here are some molecules of a solid. Yes? Okay. And the heat does this. It jiggles these molecules, which jiggle these molecules, which jiggle these molecules. And jiggling molecules mean heat, okay? Because temperature is just microscopic kinetic energy. So if you have a temperature that goes up, it's because the molecules went from going like this to going like this, okay? So fast-moving molecules mean higher temperature. All right, slow-moving molecules mean lower temperature. All right, and anyway, thermal conductivity, that's how quickly materials conduct heat, so that's heat conduction. Guess which things make good conductors? Well, silver is better than copper, but once again, why are our pots and pans not silver? Because it's expensive. Yeah, and also it tarnishes really easily, although so does copper, whatever. Concrete doesn't have great thermal conductivity. Silicon has pretty terrible conductivity, which means silicon makes good oven mitts. Yeah? And also some other things. And then air actually has pretty bad thermal conductivity. Water doesn't have great thermal conductivity, but it's a lot better than air. And that's why you can hang out in 45-degree air for a long time, but 45-degree water can kill you in a couple of hours. Because your body just can't keep up with keeping you at the right temperature for you to not die. Okay? Rates matter. Okay. So, convection, basically hot fluids rise, cold fluids sink, and then you can transfer heat by the motion of the fluids. So we've gone from solids to liquids and gases. if you have here, like we have 2 cold coffee cups and a hot coffee cup, here's a bunch of water above them with some food coloring in it, and you can see above the hot coffee cup, you have the fluid rising, and then over here, where the water's cold, it falls back down, and you get this nice circular-ish pattern, all right? And here's I just found this really fun GIF from the newwaveprooven.com, as seen on TV, okay? This is heat circulating, okay? This is called forced convection. Why is it forced? Yeah, convection just means airflow, right? And forced convection means you're forcing the air to flow, so you're moving the heat around intentionally. It's also natural convection, which means there's heat going up and then cold air falls, and so you get circulation. It's much slower. And this is called a German pyramid. Anybody seen one of these? They're very popular with fancy older ladies during Christmas time. No? You guys don't have the same mother-in-law I do? Okay. So natural convection, you light candles on this thing. What happens with the hot air from the candles? Rises. What does it do to this? Spins it. Okay? And then you have like cute little angels and things that go in a circle. And if your mother-in-law is like my mother-in-law, she buys one of these she bought like a $200 one from Germany, and she was like, it's broken, it doesn't work. And it's because she put all her fan blades at random angles. And she was like Googling, like, how do I fix this thing because it's broken? And she was like trying to return it to Germany. And I was like, it works now. So anyway, you can be a hero at Christmas if you know physics. And then we have radiation. So electromagnetic waves are emitted by all objects. Actually, you are currently emitting electromagnetic waves. What range? What are those called? Somebody in the previous class said X-rays. I was like, and the guy sitting next to him like moved away because we just talked about the cancer thing. But no, are you cold, warm? You're emitting heat, which means that is infrared radiation. Okay, so you are emitting infrared radiation. You are actually what's known as a black body radiator, but we'll talk about that later. So anyway, if you look at infrared radiation maps, wait, why isn't this working? Oh, there it goes. Here, this is a glass of hot water. Here's a glass of cold water, so you can see this is where the water's hot. These look the same. You can't even see the water, and you can't tell what temperature it is by looking at these cups, although the hot one is red. But here you can see the water looks dark. Here the water looks bright. This one's hotter. Okay. Can you see this guy's hand? No. But if you look at an infrared map, even though there's plastic which blocks the visible light, it does not block infrared. All right? What? Oh. That's great. All right. It turns out the rate of heat transfer for radiation is T to the 4th, so temperature to the 4th power. Okay, so Q is proportional to T to the 4th, and the frequency is proportional to the temperature. Okay. That's the frequency of the wavelength. Then we have, wait, this thing is, oh, there it is. Okay, so here we have actually, take a break, come back, we'll watch this short video, and then we'll finish up. And switch chapters. Come back at 1:48. What's up? Oh. Nice. That's you. Good job. Well, it's in alphabetical order. But feel free to take it personally.
Actually really easy. That's why everyone
Wear a badge.
I wear wanted to take extras.
Well, the medical business usually manage
That was actually interesting to try to see that. Yeah. My profession is like transfer over.
Somehow
School, the radiation.
it's really a prayer.
I
you
figured
know,
the radiation business
I got that today.
Lots of big use.
yeah.
It's a good job getting out the Navy.
No, it's not. No. 2 years. No, it's not bad.
I was almost making 6 big ones.
Trust me, you'll know the difference if you have $100,000 a year versus $400,000.
Well, 100,000 out of the Navy.
Low is different than mid. Especially if you're trying to buy property.
What I did was I got
That's just ridiculous. Yeah. When I was in Houston, I got a house that here it cost like
Everything costs money.
here it's terribly expensive.
They have nice places. Some of them. What's crazy is like my friend that owned the house he bought in San Jose, it was like way shittier. It's just like a regular like 3-bedroom bath, especially on it, not modern, it's just very Silicon Valley. It's the only real feature. But I was like, we paid like the same amount for our house. We stand on our roof. We look east. So we're basically garbage.
But you live here at least, right?
Yeah, I live in
Yeah, at least you live in San Diego.
No, I mean, I could live a walk.
You get marked up for?
I did some conversions.
For 2 or 3?
Well, that's living just a little bit.
My friend who lives in Boston, because he found out that he works, he could do software, and that he could get the same salary and live in Austin, buy a house for like $30,000.
Easily good.
Yeah, I was like,
What's your contingent with Texas?
not California.
Yeah, but California's so odd.
Right, how do you
How many places have you lived anywhere else out of California? Well, bias.
Yeah.
No, I know.
California's not bad.
I've been to a lot of places, but I've never
What's big? What's the
I mean, I have a lot of family that live in like Virginia and New York, Florida. It's pretty.
It's boring.
It's crazy. I really enjoy Washington State.
Oh yeah. I mean, I like all those places.
That's kind of how it felt. Luckily, I didn't compete at the time.
I really like Europe.
With Europe. You've been there? Or
Yeah, I've worked there for 2 different summers.
Where'd you go?
I lived in Poland for a summer. My husband did an away rotation in Vienna. Right before I started this job.
Did you actually go visit yet? Did you actually?
So we were living.
That's awesome.
We got like an apartment.
So we go to see you.
No. Everything's in English. But he actually spoke a fair amount of German by the time he left. He had to like use it in work, and I just was like taking our 1-year-old.
That's cool. Very
Yeah.
nice.
It was awesome. Poland was really fun because I didn't have a
Uh,
But yeah, that was like,
Yeah.
okay.
No,
That I was in Krakow. Like really cheap. So I was getting paid. Well, they pay for my house.
Oh,
But like, food and spending money, which I was living in Berkeley, so that was not a lot. But in Poland, yeah, the exchange rate was fantastic. I was like, I'm gonna buy $5 lunches. And those are like the fanciest lunches in Poland.
I've been there.
And all the like grad students I was working with were like, "What? We can't eat this restaurant. It's fancy." I was like, "It says this is $5."
It's literally gonna be like $2. It's like,
Beer was like a half liter for $1.
you know what they did though? When we pulled to port, everything's supposed to be really cheap. And then usually raise the price by like 3 or 4 times. So when we get in there, oh, they would always any sweet.
The great thing about being in Poland is that there was no, well, the good and bad. Zero American like not in like 2005. And I think I saw 2 Americans in the entire summer that I was there. And I was there by myself. I had to hang out with them. So like, you know, we can talk about like the weather and like but I think like have a serious conversation with anyone that is depending on how to work that we had to tell them. It's awkward. And then the French people would only speak in English with me if I could get them across. Otherwise they always speak in French to each other. So yeah, like I was on this bus and I heard like a text. Oh my god! Please talk to me. Which normally I'm not that attracted to. Like, please don't.
Yeah, that's what I'm saying.
Yeah, so it was an experience. Something about like being completely alone or surrounded by people who don't know that's good. You get really good at doing things for yourself.
So I remember like I had to start drinking sparkling water because I like messed up the word for, because like all of their water, yeah, all of their water was bottled, and I didn't know how to tell which was sparkling and which was flat, and at the time I didn't like sparkling water. I thought it was gross, and I went to the store and I bought all this water because you can't drink the tap water, and all of it was sparkling, and I was too embarrassed to take it back, so I like drank sparkling water for like 2 weeks.
The tap water turned terrible out there.
Yeah, actually, I mean it was like you had to boil it if you were going to use it. I mean it didn't have any lead in it as far as I know, so. Yeah, I don't mean like it tasted bad. I mean like you would be sick. Like,
Drinking it out there.
yeah, I mean, depending on your like how countries manage their water supply, like it can get contaminated, and then you just can't drink it out of the tap. Like we really take that for granted here. It may not taste great, but
I mean, what about bathing in it?
Lesser influence.
what?
Bathing in it.
But what about what?
Bathing in it. Like taking showers.
Oh yeah, just like don't drink it in the shower.
Why were you in the shower?
Just don't shower like this.
Why were you gargle in the shower?
Yeah. Okay, so hang on. Oops. Oh, we're gonna watch this video. What? All right. We're gonna watch this. I just want to warn you before I start this video that I think it was made in either the late 90s or the early 2000s, so it looks a little dated, and somebody got really excited that they could do transitions in the video between scenes, and the graphics are what you would expect for that era. But it's a good video, so we're gonna watch it anyway. No, nobody's made a better one that's less cheesy.
These days we're all familiar with night vision cameras, but how do these things work? How is it that you can just turn on this camera and see the invisible? Another use of night vision cameras that you might not be familiar with is their ability to see through smoke and dust. Fire departments commonly use cameras like these to find people trapped in smoky rooms, or to pinpoint the exact location of forest fires through clouds of smoke. So how do these things actually work? What are we really seeing when we look inside a night vision camera? Well, it may surprise you to learn that everything in the universe emits some kind of light. It's just not the kind of light we're used to thinking about. The sun, for example, our star, emits visible light. That's why our eyes evolved to detect that kind of light. But that's not the whole story. I'm sure you're familiar with all the different kinds of visible light, all colors from violet to red. But there are actually lots of other kinds of light that our eyes aren't sensitive to. The reason all the colors of light are different is that they have different energies. And what you see here is that the light has different wavelengths. The blue light, for example, has a higher energy, so it has a shorter wavelength. The red light, on the other hand, has less energy, so it has a longer wavelength. But that's just the light we can see with our eyes. That's not all there is. The shortest wavelength light are gamma rays, which can have wavelengths smaller than an atom. The longest wavelengths are radio waves, which can have wavelengths larger than the entire Earth.
No, this worked like earlier today. Cool. That's fun. Sorry, I'll run it back a little.
That's what light is called, infrared light.
I don't know, she's showing the mouth though.
It looks a lot different than infrared light. Remember that what you're actually seeing is temperature. Something that's warm is going to look bright in the infrared. And something that's cold looks dark. Ice cream.
What?
Blow dryer. And infrared radiation is actually a measurement of temperature. Places on my face that are cold, like my nose, appear dark in the infrared camera because they're giving off less infrared radiation. And places that are warm, like my mouth, or the hair next to my head, are brighter because they're warmer. You can even see my breath in my nose if you look carefully. And this is an ice cube. And humans, of course, are not the only things that emit infrared light. What do you think you can learn about animals by observing them in the infrared? What about reptiles? Remember, they're cold-blooded. Giraffes. Here's a Nubian ibex. What do you think horns look like in the infrared? Can you even see a gorilla in this picture? If you look carefully, you'll notice you can still see the zebra stripes even in the infrared. How about elephants? What about a polar bear? How about a rhinoceros? Check out the horns. All right, a cat. Notice the infrared footprints. Deer in the dark. A helicopter. Notice the plume of heat from the engine. Earth movers with hot smokestacks. A car engine turning on and heating on. Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light entirely. I have a black plastic bag, and as you'll notice, you can't see through it at all. But with an infrared camera, there's no problem. But just like infrared light can penetrate some things that stop visible light, it also gets stopped by some things that let visible light through. For example, here's a piece of glass. And as you can see, none of the infrared gets through at all. If you haven't guessed, that's how the greenhouse effect works. Infrared light can't get through gases like water vapor in our atmosphere, which means that the heat is trapped and our planet is getting warmer. So what am I, an astronomer, doing with an infrared camera? Well, if everyday objects look different through an infrared camera, you can bet objects in space do too. For example, here's an image of the constellation Orion, which you're probably familiar with from the night sky. But now, let's look at it through an infrared camera. Look how much you're missing. Astronomers are also hoping to use infrared light to find planets around other stars. Planets don't give off any visible light of their own, making them nearly impossible to see close to a bright star. But in the infrared, planets give off their own light, making them much easier to find. Astronomers will soon be able to use very sensitive infrared cameras on a new space telescope, the Space Infrared Telescope Facility. And it gives a whole new perspective on the universe.
Yeah, it's like up there.
At that point, we'll finally be getting a more complete view of the universe. Right now, we don't even know what we're going to discover. There are so many wonders out there. We'll finally be able to see more than our eyes can see.
The music is so good.
Music by Jeff.
I know. I
wonder if he's on the spot.
I can't remember what year this is from, but it's old. Yeah, so sorry about the production quality of that video, but aside from the two like modern applications, which are now like 20 years behind because that satellite went up that telescope went up a long time ago, and we found like literally thousands of extrasolar planets now, and the main guy who found them is super rapey. But he got fired a little bit. But he's still really good at finding planets. So I guess there's that. Radiation, just if you think about Earth, okay? Light comes in from the sun. It's mostly in the visible range, also a little bit of UV, which is why you have to wear sunscreen, a little bit in the infrared, okay? What gets through the atmosphere? Mostly visible and a little bit of UV, right? Even there is some stuff in the infrared range, and that bounces off. Okay, so if the Earth didn't have an atmosphere, this stuff would come in, it'd heat up the Earth, and then what does the Earth give off? Infrared, right? So the light hits the Earth, okay? It heats up things like water, soil, people. If you stand in the sun, you can feel yourself heating up, right? Some of the light just bounces off you, so visible light can just bounce off you, which is why I can see you, right? Visible light bounces off you, that's what we see. Some of the light gets absorbed, and that comes back out as heat, okay? So this is the energy radiated by the Earth. So the light hits the Earth heats up, it radiates infrared, okay? If you didn't have an atmosphere, the temperature on the surface of the Earth, based on energy considerations, like how much light from the sun hits the Earth, how much it heats up, would be about negative 22 degrees Fahrenheit. That would not be a very pleasant Earth to live on, so it's good that we have an atmosphere, okay? This is actually the temperature of the outer atmosphere, which is how we know that's true. You can check that, okay? You can send something up there with a thermometer and be like, okay, that's the temperature, okay? So outside the atmosphere, we're at about negative 22 degrees Fahrenheit, okay? If you put this back in, well, instead of escaping out into space, infrared doesn't go through the atmosphere. So it didn't come in from the sun, right? All the infrared bounces off coming in from the sun, but any infrared radiation we produce from the Earth, okay, gets trapped because it can't leave. So it just bounces around. And this is what we call the greenhouse effect, okay? Whether or not you're subscribing to climate change, this is just why the Earth is warmer than it would be without an atmosphere, okay? And the chemical composition of the atmosphere is what determines which wavelengths of light get through and which ones get trapped, okay? So if we change the chemical composition of the atmosphere, we change the balance of how these things work. And we can also create more heat in the Earth on our own by using other types of energy that aren't solar, like, you know, burning dead dinosaurs and things like that. And that changes the whole picture. But this is the basics of how it works. Like, for instance, Venus also has an atmosphere, but it's not a place you would want to live. Okay, it is a little bit closer to the sun, but it's significantly hotter, not in proportion to its distance from the sun. And it's hotter because its atmosphere is made of such a dense gas that a lot of light doesn't even get in, but light that comes in gets trapped forever. There's lots of heat going on, and it gets super hot under their atmosphere. Okay, so there's and then, you know, Mars has a very sparse atmosphere, so it's very cold. There's lots of different factors, but basically the wavelength of light matters. Certain chemicals, certain molecules absorb light or reflect light at different wavelengths. Okay, so the wavelengths that come in are not necessarily the same as the wavelengths that go out. Okay. Also, heat transfer in the human body. Remember, air is a poor heat conductor. Okay, water is also a poor heat conductor, but it's better than air, which means if you're in cold water, you die a lot faster than if you're in cold air. You can hang out in 45-degree weather, even naked if you have to, forever, essentially, without dying. But if you're in 45-degree water, you have about a couple hours. And if you drop that 10 degrees, you can get down to minutes, okay? 35 degrees is pretty cold. You might want a sweater if it's air. If it's water, you can die within an hour, okay? So that, and there's some chart if you want to look at that.